I'm gonna record this for the rest of, so I can post it also. So yesterday, we already talked to, we don't even need the calculator for this one. That if you have a 2 by 2, 3, 5, 4, 6 times another matrix, and that's a capital A matrix, because you could just multiply by 1, the number 1. But if it's a matrix, you have to use the matrix identity. So a 2 by 2 identity, A would have to be, it's 1, 0, 0, 1. It's that diagonal of ones. Same thing here. If it's a 3 by 3 times a matrix and you get the exact same 3 by 3 back, then that 3 by 3 is going to be 1, 0, 0, 0, 1, 0. Oh, how did that get over there? 0, 0, 1. So, and that's called the identity. It doesn't change. 2 by 2 identity, 3 by 3 identity has to be a square matrix. We'll use that identity in future problem solving stuff. So the inverse is what could you multiply this matrix by to get the identity. If it's the inverse, you can multiply it in front or in back, doesn't matter. But to get the inverse, and I have both of these written down, so I'm gonna do them both on Desmos when I go over there, and then come back and we'll write the answer. So in Desmos, you're going to do a new matrix. First one was a 2 by 2, so I can put 7, arrow 2, arrow -3, and 4, and enter. So you want to type the matrix in and enter, and then whatever matrix name it is, which is A, you will inverse it to the -1 power. That's the inverse button. That's the reciprocal. And you're going to get this many times, fractions or decimals and stuff like that. That'll change it to a fraction. The common denominator will be the greatest one in all of these. So 34 is the common denominator. So I want to multiply 34. And that way, it'll take it down to, you can see they just switched the 4 and the 7. They did the opposite of those two numbers like we talked about. So you'd write it as 1 over 34 times that matrix. That's the inverse. So
Mr. Rakowitz,
yes.
how do you find the 34 again?
When you just do the inverse, see how they're all fractions? You have a 17, 17, and a 34, and a 34 is your denominator. Your common denominator is going to be the larger of any of the fractions because they're all going to be multiples of each other when you do this. So whatever the largest denominator is of any fraction, that will be the one that will take all of them out. That's
okay, thank you.
Yeah, 34. So B is a 3 by 3, so you got to change your rows and columns. And B was -2, 3, -4, 5, 1, 4, 3, -2, -1. And enter, so now it knows what B is. So I'm gonna raise B, because when you put B, you'll see it back. Check, make sure you put them all in. So -1 power. Again, that's all, I'm gonna make fractions. And there, my largest is the 117. I'm gonna multiply by 117. And like I said before, that number that goes out front also is the determinant. So if I just did the determinant of B, you'd see it's the 117. So you might want to look at the determinant first just to make sure if you know it's positive or negative, because that determinant could be negative. All right, so back to that whiteboard for a minute. Okay, so like I said, that 1 over 34 times 4, -2, 3, 7 would be the inverse of that matrix. And this one was 1 over 117 and 7, 11, 16. So I cannot look at these and they're not just switched around. Doesn't work. So finding the term or the inverse of this matrix is a long process. So we are going to do it with the calculator every time. 1710 -28, 1710 -28, and -13, 13, -13, -13, 13, -13. That's it. So inverse. Now, there are some matrices. Say I have 4, 8, 2, 16, right? So if I try to find the inverse of this matrix, so do a new matrix, and it was 4, then a 16, 2, 8. Matrix C. So the matrix C inverse is going to give me this error because this matrix doesn't have an inverse. And the reason that is, if you look at the determinant of C, it's 0. And if the determinant's 0, you can't write 1 over 0 for your, so the denominator of all those would be 0. And that doesn't work, right? You can't divide by 0. So there are matrices that don't have determinants or that don't have inverses because their determinant is 0. And as you get into higher level mathematics, when you talk about encryption, you've heard of encryption and stuff like that, they encrypt things using matrices, and the way they make it where it's safe on the internet and stuff like that is they use matrices that have determinants of 0, so you can't decrypt it or decode it. But that's later. Maybe get into that in college. Okay. So back to that whiteboard. I'm going to skip this determinant. You've seen that. I don't need to go back to the, we've done the determinant a few times. Just type it in your Desmos and use that determinant. Okay, so this, when you find the area of a triangle, so if you think about this problem, you have this triangle out here in space, 2, 5 would be one of the points, -7, 8, and 5, -1. So you have this triangle. And if we had to actually find this dimension by hand, or find this area by hand, we'd have to pick a base, right? Say we use this part as the base. You'd have to find the distance of that using the distance formula. Then you'd have to get a perpendicular line that went from that vertex down to that base using slope. and a line through a point, and then find the distance of that line, and then 1/2 base times height. And that's crazy geometry stuff. But what they figured out is that there is a simple formula for the area of a triangle using matrices when you know the 3 vertices. And those 3 vertices can't be collinear, because if you had 3 points in a line, it wouldn't make a triangle. And you would get 0 for the area. And if you get 0 for that area, you know those points are in a line. So you take 1/2 and, oh, not the matrix, but the determinant. Where's my eraser? I can hear all of you, don't do the eraser, it takes forever. But, okay. So you take, and it doesn't matter which order you put these in, you take each coordinate, take the x and the y of each coordinate. So take the x of the first coordinate, y of the first coordinate, and the last number is always 1. Take the x, the y of the second coordinate, 1. Take the x and the y of the third coordinate, 1. If this number happens to be negative, then just change it to positive. It's really the absolute value of all of that. So if it does turn out to be negative, just make the positive. So in your calculator, you just put in the matrix, which is a 3 by 3, and you do 2, 5, 1, -7, 8, 1, 5, -1, 1. And that's it. So let me, do I have that here? Yeah. So back to see how that works in Desmos. So again, I'm not going to use any of those. Remember, once I clear all, I can't call back up that A matrix I already typed. So be careful about clearing all if you plan to use the matrix again. So I need a new matrix. It's going to be a 3 by 3 for any triangle problem. And just do your vertices. And again, it doesn't matter which order they go in, as long as you do the x and the y of the same point. And then a 1 in the last column. So the next one was -7, 8, 1. And the last vertex was 5, -1, 1. So you have your determinant. You can type in 1/2, or you could make sure you arrow to get out of the denominator. You could have just typed in 0.5, right? Times the determinant of matrix A. So the area of that triangle would be 22.5 units squared. And it's that simple. The answer is just 22.5. And if it told you what the grids were, like inches or whatever, if not, it's just units squared. So same thing. If I have 3 points that are collinear, so collinear points are easy. Like let's say I start with 2, 5, 1. As long as I increase them both by the same amount each time. So if I make the x's go up by 2 and the y's go up by 3, then that would be my slope, right? That's 3/2 is the slope. So I got to go up by 2 again, up by 3 again. So those 3 points would all be collinear. They're right on that line of with a slope of 3/2. So 1/2 of the determinant of B, and you see, you get 0 because those 3 points are in a straight line. They don't make a triangle at all. So this could also be used as a way to check, are 3 points collinear, right? If 3 points are in a straight line, then they would give you, you just have to, you don't even need the 1/2. If the determinant was 0, then the points are in a straight line. All right. So the next one, I'm not going to go back and show. The next part of it was transposing matrix. And transposing just means that you take each row and that becomes the new column, right? So if you look at B, instead of doing 2, 5, 1 across, the first column would be 2, 5, 1. And the second column would be 4, 8, 1. And the last column would be 6, 11, 1. You transpose it, the diagonal would always stay the same. So, and there's a button, this to the T power is transposing. So if I want to transpose B, I would do B transposed. Like I said, it just switches, and now each row became each column. If you want to transpose A, it's A transposed. So the one that's on your notes is a 2x3, so a new matrix, 2x3 with 5, -8, 2, and -6, 7, 3. So if that's a 2x3, then transposing it would make it into a 3x2. It's going to switch. So C transposed just makes it first column, or first row becomes first column, second row, second column. That's all transposing does. And it's useful sometimes when you have the right information, you just don't have it set up in the matrix right. So you might want to multiply times the transposed matrix. Any questions on transposing? I think that's fairly straightforward.
Can we transpose a matrix to multiply with another one if it didn't work in the first place?
Yes. So like I can't do A times C because they don't match up. But I can do A, which is a 3x3, times C transposed, because that would then be a 3x2. But you still have to be careful about when you transpose the matrix, are the things you're multiplying together making sense? And sometimes it will not make sense to transpose it as far as what they represent. But yeah, you can transpose to multiply them. All right, where am I? Okay, so let's go back to so know that formula. Remember, just don't forget the 1/2 for your area of that triangle. You got a few of those problems on your worksheet. Lots of determinants, that's easy. Transpose, we just did that. Transposing, you don't have to have the calculator to transpose. I mean, it's there, but if you're transposing this matrix, you're just doing 5, 8, -3. First row becomes first column. So then 6, -2, -1, 4, 3, 7. But if you're working in some operations and stuff like that. Okay, so here's one of the really useful things with matrices that they don't teach you in Algebra 1 and Algebra 2, which would have been nice. But solving systems of equations, if I did this system of equations by hand, I would first have to, if I'm going to use elimination, I'm going to have to multiply so that, like, I want to match up the y's. So I'd multiply the top one by 4 and the bottom one by 3. So I'd get 12 on. So it'd be 8x plus 12y equals 64. And then 15x minus 12y equals 3 times 17 is 51. Doesn't matter because I'm not going to finish this. Then you would add them together. That would eliminate the y's. You could solve for x. Then you plug the x back in and everything. When that gets to a 3 by 3, it takes, we did a couple of those earlier this year, right? Where you had to solve 3 variables with 3 equations. Well, if you use matrix, we can represent this equation as a 2 by 2 matrix, which is your coefficient. So 2, 3, 5, -4 times x, y. So like if I said to multiply these two together as a, if I just like a quiz question, remember it's first row times first column. So it'd be 2 times x plus 3 times y. And then the second would be 5 times x minus 4 times y. So that's exactly what this is, just written into matrix form. You're just separating the variable from the numbers. What that equals is this 2 by 2 times a 2 by 1 will give you another 2 by 1 of 16 and 17. Erase this part. Takes forever. So to solve that equation, to make this into an identity matrix, I need to multiply it by its inverse, 2, 3, 5, -4. If I did the inverse of that matrix and multiplied it by this 2 by 2, I'm going to get 1, 0, 0, 1 times xy, which 1 times x would be x, 0 times y would be 0, 0 times x would be 0, 1 times, so that would just leave you xy. So what I do on one side, I have to do on the other side. And since this is a 2 by 2, and that's a 2 by 1, it has to go in front. So you have to take and do your inverse, the 2, 3, 5, -4, inverse times your solution. And that's always going to work with these systems of equations. So before I move on, or before I go over to Desmos, to solve for this 3 by 3, or 3, equations, 3 variables, I'm going to take all the coefficients, which are 5, -3, -6, make sure that it's in the right order, x, y, z, so 3, -1, that would be a 1 there, -5, and 4, -2, -1, right, that'd be a 1 there. And I'm going to multiply that by the solutions, which are -4, 5, -13. And the answer I get will be the x, the y, and the z. So now I'll go over and show you both of those on Desmos. So the first one I'm just going to clear off. So my first matrix was, remember, you don't have to do the inverse, or you don't have to type in the inverse, just type in the regular matrix, 2, 6, 6, -3. Type in your second matrix. Oh, type in a new matrix, which this was a 2 by 1 of 22 and 24. Once you have your two matrices typed in, that's the coefficients, that's the solutions. You do the coefficients to the -1 power times the solution matrix. So my answer for the first one is x equals 5, y equals 2. And it's so much easier. So if I'm going to do that 3 by 3 of 5, -3, -6, 3, -5, and 4, -2, -1. Then I need that 3 rows by 1 column for my 3 solutions of -4, 5, and -13. And then same operation. So take your coefficient to the -1 power times the solution matrix. So in that one, x equals -2, y equals 4, z equals -3. All right. So back to that whiteboard. But yeah, so if you remember early in the year when I was making you solve those 3 by 3s, I forget what we were doing. You don't have to solve them by hand if you have the matrix stuff, right? So when you type that in, the x was 5 and 2. So x equals 5, y equals 2, or those two lines cross at the point 5, 2, right? Yeah, so forgot the -1 there. That's very important. So the inverse of this one times will equal x, y, z. And it turned out to be -2, 4, -3, and you're done. So much quicker with matrices. So on the notes, it says, if we were in class and we had a lot of time, I would have had you solve those by hand first to remind you how painful that is, and then showed you how to solve with inverse matrices. But since we are on limited time, I just jumped right to the inverse matrices. So same thing, and hopefully you guys, if you're going to put this one in to the calculator, it'd be 5, -4, 2, 1, 5, -6, 1, 4, -5 to the -1 power times 21, 24, 21. And that'll give you your solution. If one of these is not there, if you had a system equation that was like 3x plus 2z equals 7, and then 5x plus 3y plus z equals 1, and 8x plus 2y equals 5, right? When you set up that coefficient matrix, the 3 is the x. If there's not a y, it's a 0, and 2 is z. So only use the 1 if there is one there and it just doesn't have the coefficient. If there's no variable there at all, it's a 0. That'd be 5, 3, 1. And then the bottom one, there's a x, there's a y, but if there's no z, 0 to the -1 times. And I'm sure that doesn't come out to a nice solution, but just to show you. All right, so the other one, there's a Kramer's rule. So back when I was in high school, which would have been 83 through 86, so many years ago, back when we used chalkboards, we didn't have matrix calculators, and finding the inverse, like I said, finding the inverse of a 3x3 is a nightmare when you're doing it by hand. So we used Kramer's rule. Now this is outdated. It's kind of nice because Kramer's rule will find exactly one of the solutions. So it says use solve number 8. Where's number 8? I got it here. Oh, it's not number 8. It actually should say number 9. So number 9 was 2x plus 6y equals 22, and 6x minus 3y equals 24. So in Kramer's rule, you just solve for one variable using the determinants. And the way it works is the denominator is always the coefficients. So it'd be the 2, 6, 6, -3. That's the coefficient matrix. And then the top one, if we're solving for x, then you take the x's, the 2 and the 6, and you replace them with the solutions. So I'd put 22 and 24 there, and then I would leave the 6 and the -3 the same. The y's is the same. So it's just determinant over determinant, and that'll give you the x value. Now we know x is 5. I'm going to show you how that works, but then you solve for y separate. And the y, the denominator is still the coefficient matrix, 2, 6, 6, -3. But to solve for y, you leave the x coefficients the same in the numerator, and you replace the y's with the solutions, the 22 and the 24. So if you're over here, just clear all. So if I have that, I'm going to start with, oh, get rid of that. My new matrix, I'm going to start with the coefficient matrix, right? The 2, 6, 6, -3. That's going to be my denominator matrix. It's for both of them. For my second matrix, I'm going to do to solve for x. So that was, replace that with 22. And that's still 6, 24, -3. And then my C matrix, I'm going to do the same thing, but I'm going to leave the x's the same and change the y's to the solutions. 22. I don't know why it keeps on giving me 3 2's when I do that. That would be 6, right? And then 24. Okay, so I got my matrices in to solve for x and y. Now, if the problem said just solve for y, then you just need to do the y one. You don't have to do all of that. Remember, it's always the determinant. So x would be the determinant of b in your parentheses, divided by the determinant of your coefficient matrix, A. And you'll see that gives you 5. We already knew that was the answer for x, but you can get it that way. To get y, you would do the determinant of C divided by the determinant of A. And that's 2. So x is 5, y is 2. And the reason, like with calculators, it's so much easier to just do the other one, but it's easy to find the determinants of these by hand if you had to. But back when we couldn't do matrices in the calculator, and that's definitely true about a 3x3. So let me share. Okay, so the next one says solve. I'm gonna jump up here to 13. Oh, it's 8:40 already. So I'll show you this real quick and then. Okay, so this last one. When you have a 3x3 and it says use Cramer's rule, then it's the same idea. If you want x, you do the coefficients, which would be 1, 5, 5, 4, -5, 4, 1, 5, -1. And then to get x, you replace that first row with -2, 19, -20. Those solutions. So the second row stays the same, 5, -5, 5, and the 0 stays the same. When you type that in, the determinants, then it will give you x, and it's division. So to do y, the denominator stays the same. I don't need to type it or write it every time. But then instead of replacing the first row, you would leave the 1, 4, 1 for the x's. You'd take out these 5s and replace those with -2, 19, -20, and leave the z's, 5, 4, -1. So then z, that denominator is the same, but now the 1, 4, 1 for the x's stays the same. The 5, the -5, 5 stay the same. It's the -2, 19, -20 for the numerator. And when you divide those, you get each one. So since this process is a lot more than just doing the inverse process like we did, you'll see the questions will be just like, what number should, like in here, if I left this out, what number should go there to solve using Cramer's rule, stuff like that. Because it would just say solve this using Cramer's rule, then you should solve it using inverse and just claim you use Cramer's rule, unless it show your work. All right. So that is